In this prep assignment, we're going to talk about quality assurance, or the steps we have to take to get the right answer for our purpose with the requisite amount of precision and accuracy. This process is aided by writing clear objectives for how the data will be used, which may include certain specifications. The specifications for an analysis will tell us how good the numbers need to be. Good specifications will describe the selectivity of the analysis, or how well we need to be able to identify the analytes while avoiding interferences, and the sensitivity of an analysis, or the ability to respond reliably and measurably to changes in analyte concentrations. Sensitivity also ensures that we can measure concentrations low enough that our detection limit is lower than the expected sample concentrations. There are three types of blanks that help us determine the robustness of our analytical methods. A reagent blank is the simplest type of blank to prepare, as it contains all components except for the analyte. A better choice is to prepare a method blank. This blank is the same as the reagent blank, except it's been taken through all the steps in the analytical procedure. Our most rigorous type of blank is the field blank. This blank is the same as the method blank, except it's also been exposed to the testing site. So why might that be important? What if you were living downwind from this crematorium and you were concerned about pollutants in the soot being emitted? If you wanted to get an accurate measurement, you'd want to expose an air filter to the surrounding area upwind from the smokestack. That way, you'd be able to discuss what contaminants are being emitted from the funeral home and what may be due to other sources in the field. We can also work to guarantee the validity of our results by spiking replicate samples with a known quantity of analyte. This allows us to see how much of the analyte we're able to read back on the instrument. If we're not reading back a significant amount, then we know that we need to troubleshoot our sample prep, our analysis, or both. The volume of the spike added needs to be small so that we don't change the analyte concentration in the sample significantly. The book suggests adding a 50.5 microliter spike of a 500 microgram per liter standard to a 5 milliliter or 5,000 microliter sample. Using our dilution calculation, we can calculate that this would result in an increase of 5 micrograms per liter of the analyte. Now in practice, it's not typical to see a pipette that adds 50.5 microliters in one shot. It's more likely that you'd add 50 microliters than a 0.5 microliter of the standard. We'll see, though, that every additional step increases the amount of uncertainty in our measurements. So let's look at a more realistic method for spiking a sample. Let's consider this alternate procedure. What spike concentration results when you add 50 microliters of a 500 microgram per liter standard to the sample? Running through the calculations, we see that the spike concentration is only reduced by a tiny amount compared to the 50.5 microliter addition. As long as you know the amount that you've added in your spike, the percent recovery can be calculated. What if we added a 5 microgram per liter spike to a sample that already contains 25 micrograms per liter of analyte? When we analyze the sample, we see that the spiked sample reads 29.5 micrograms per liter. Using the equation, what is the percent recovery? The percent recovery is 90%, which may or may not be acceptable depending on the specifications set forth prior to running the experiment. In addition to spiking the occasional replicate sample, we'll want to include additional quality control samples, such as calibration checks, to determine if the instrumental response has drifted from the initial calibration. Sometimes, especially in industries with heavy regulations, analysts will be presented with performance test samples, quality control samples, or even blind samples to guard against bias. It's also not uncommon in industry to see analytical results graphed on a control chart. In this control chart, we see the warning line and action lines graphed at certain intervals above and below the expected mean.